So we've introduced this idea of a truss. Now notice back here, I've drawn these all as triangles. You often will find trusses to be very triangularly, if you will, in shape. And the reason for that is triangles don't flatten. If I have something that is kind of square, it's easier to flatten that. But if I have a triangular shape, they tend to be very stable. If I apply a stupid amount of force up here, then that is likely to hold that up. It can be distributed then amongst these other members if I have a very large force up here at point B. Now, again, we've introduced this concept of the two-force member. And so the direction of the force is known. It has to be directed along the line, along the axis of the slender member. And so what happens then is truss. I have a fly that's flying around. He may pop up on the screen occasionally. Truss members are in tension or compression. This one, for example, is in compression. Get out of here. This one is in tension. That means the forces are either pushing or pulling at the endpoints. So those are kind of the main things I want to talk about. There are truss. There are two methods for analyzing trusses. There are probably more. I'm sure there's more. But in what we're talking about here, we're going to talk about two methods for analyzing trusses. One is what we call the method of joints. The second, we'll talk about later, is what we call the method of sections. So we start with the method of joints. So the method of joints. Step one, solve for reactions on the entire truss structure, if possible. Now, unlike the problems in Chapter 5, where they're almost always possible, because that's the goal of a Chapter 5 problem, is almost always to find the reactions. In Chapter 6, we might be in a situation where the reactions cannot be found immediately. And we'll see that. It's manageable. We now will have more ways of getting to the reactions eventually. Solve for the reactions if possible. Step 2, draw free body diagram of a joint. Need at least one known force. So draw a free body diagram of a joint where, not necessarily need, it's just where you have at least one known force, and no more than two unknown forces. joints continued. Lecture 11, page 3 of something. Currently we're on 3. No more than, so one known force at a joint, no more than two unknown forces at a joint. Once you've done that, because I've got a free body diagram with two unknowns, that's solvable with just forces in the x and the y direction. So we're going to solve the equilibrium equations for the two unknowns. And then step 4 is move to another joint with no more than two unknown forces. And then repeat until you have analyzed each joint or you've found all of the unknowns for which you are seeking, so to speak. So how does that work? Well, let's look at an example, shall we? We got enough time. I don't know if we'll finish the example in a reasonable amount of time, but we'll get at least started on the example. Which, by the way, notice that that doesn't look too terribly unlike this guy that I said, remember this, is we're going to see this over and over again. And I carry that thing around with me while I'm teaching this class. Yeah, it looks very much the same. That's by design. There's a reason for that. All right, so let's look at an example, shall we? Example. I'll show you what I'm going to draw. This guy. Oh, this guy. We're going to draw this guy. Okay. Simple triangle. Very simple truss problem. Draw a vertical member here. We'll put it on a pin. We can put this first member outside the pin. That's kind of a weird way to do it, but we can do that. Second member we'll put underneath the pin. Comes over a little ways, about as tall as it is wide. We'll put the second one over here on a roller. Put a pin there. And we'll draw a member coming from here to here. Pin at the top. You can't see any of that. Why didn't you guys tell me that? So, something like this, right? So, vertical member, you can draw the horizontal member in here next. This member then coming down at an angle, put it on a pin on one end, a roller on the other. We'll label these simply point A, B, and C. And then we're going to apply a simple horizontal 500 Newton force up at the very top. We're going to say that this thing then is 2 meters tall and 2 meters wide. And the problem is going to ask, find the force in each member and state if they are in tension, well, you can just call that T, or compression, we'll call that C. And I'm looking at my time. I think I'm going to stop this video here, and we'll pick this up and we'll just work all the way through this video on, or this problem on the next video. So let's do that, okay?